So in the next hour, the next hour was called light-induced superconductivity, which is a term that we use for various phenomena that we have observed in superconductors, in which excitation of some phonon creates a transient state in which at least some features, let's say in the optical spectrum, are very similar to the ones observed at equilibrium at low temperatures in the same material in the superconducting state. And we observe these features when the system is excited at very high temperatures. So in principle, these are experiments in which it seems that this phononic excitation resurrects some properties of that the system had at lower temperatures. Okay, and so it's something that could be either in. I'll elaborate more later. Okay, so the next part is going to be phononics in superconductors, basically. And the reason why one might be interested in phononics in superconductors is, let's say, even very generally, one could say that in some materials, such as the high TC cuprates, one knows that some lattice distortions are sometimes instrumental in quenching the superconducting transition temperature. This is, for example, known at specific dopings in some cuprates, in which at specific dopings one has, for example, stripe orders that become the ground state of the system and quench the equilibrium superconducting state. And so in that case, one may think that by unquenching, by exciting the phonons in the correct way, one might be able to melt these competing orders, as I will elaborate on later, and increase TC. A second reason why one, without knowing anything, might think that exciting phonons might be useful in superconductors is that it's actually known that phonon fluctuations in the right way are actually good for some superconductors. So this is some picture that depicts the attractive interaction in a classical superconductor in which the exchange of phonons might can create pairs that then condense that then form the superconducting state. Okay, so again, this is an extremely broad view of what one could do, but it kind of justifies very broadly why one wants to study nonlinear phononics in superconductors. Okay, let's start with the first one of these two. So the cuprate superconductors, again, are these materials that are these perovskite-like oxides in which copper atoms are hosted in oxygen octahedra. These copper atoms form planes, copper-oxygen planes, and the stoichiometry of the system is controlled by these other dopants. And one can plot these phase diagrams that become more complex every time one looks in these papers. This is something, one incarnation of this. One has a temperature here and the doping, which is how many, what the valence of the copper atom is. And for very small dopings, one has antiferromagnetic order at doping levels between, say, 5% and way beyond the 15% of optimal doping. One has this high temperature superconducting state that appears to be coexisting or competing or intertwined, etc., with the other types of order that either help it or quench it. And so in some cases, it's known, as I mentioned before, that these orders are actually enemy of superconductivity. And this is, for example, the case in this europium doped lanthanum strontium cuprate at 1/8 doping, in which when one goes at 1/8 doping, one finds this stripe order in which one particular distortion of the oxygen octahedra, which has got to do with a tilting of these octahedra with the correct spatial periodicity, that this particular distortion underpins the stripe order that quenches superconductivity. Okay, so when we started thinking about this, we said, okay, maybe if we shake these phonons right, we can take the low temperature tetragonal distortion, which down here quenches the superconducting state, and pull it straight and melt this lattice order, and then make the system superconducting. Okay, so the way we started doing experiments was by pumping, again, one of these high-frequency stretching modes. There's actually, as I mentioned in the first lecture, there's technical reasons why up to now we've only pumped these high-frequency modes close to 600 wave numbers. And this has got to do with our ability to generate laser sources which are intense enough at the right frequency to drive whichever mode we want. The situation is changing, but for many years we've effectively only been able to excite modes at frequency higher, at 600 wave numbers or higher. So that's why we've only excited these modes up to now. Okay? But let's say that we take one of, this is a cartoon picture of a stripe compound that quenches superconductivity, and we can excite this particular mode at 600 wave numbers with microjoule pulses and many megavolt per centimeter fields. They can now drive this infrared active in-plane distortion now in the single layer cuprates and try to melt this. And so then we ask the question, can we take the system and turn it into a superconductor at a temperature that is higher than the equilibrium transition temperature? Okay, so how can I tell what are the finite frequency features that tell me that a system is a superconductor? Of course, a superconductor is strictly defined, is only an effect that happens at zero frequency, which from its magnetic properties, of course, because it's a DC diamagnet, and because it has a zero resistance at zero frequency. And everything else that I see at finite frequencies is indirectly related to the superconducting state. But there are some features that, at least at equilibrium, are considered one-to-one synonymous with superconductivity, just anecdotally, let's say. And one of those is the observation in the optical properties of these cuprates of these plasma edges at about 1 to 2 terahertz frequencies. This is something that was the subject of the last lecture, but I will just briefly recap what the presence of this Josephson plasma edge tells me about the superconducting state in cuprates. If I measure the terahertz reflectivity with an electric field perpendicular to the planes in cuprates, what I will find is that in the normal state, if I think about these planes, these are the copper-oxygen planes. In the normal state, the way I can think about the electrodynamics at these frequencies is one in which I have capacitances in the plane and resistive transport between the planes. So what I will find is that if this is an RC coupled system, and the frequency-dependent electrodynamics will be featureless. The Fourier transform of an exponential will be something that has got no features. When I go in the superconducting state, what will happen is that the Cooper pairs will tunnel between the planes and will short this resistive transport. Okay, so to zero order, I can think of the electrodynamics of these cuprates perpendicular to the planes as some LC type coupling, which has a very clear resonance, which is at 1 over square root of LC, and this gives rise to oscillatory tunneling of Cooper pairs between these capacitively coupled planes. Okay, so if I now measure, I will find a very specific resonance in these cuprates at one specific frequency, which is related to the density, is related to the capacitance of the planes, is a number of things, but everything else being equal, the exact frequency at which I find this is related to the density of Cooper pairs in the planes. Okay, so this is if I take an optimally doped lanthanum-strontium cuprate material and I cool it down at equilibrium, I go from the red curve reflectivity, from the black flat reflectivity. Age is really not my friend here. From the black flat reflectivity to the red reflectivity, which shows a plasma edge. Okay, with this plasma edge being at a frequency which is 1 over square root of LC, where L is related to the number of Cooper pairs. Okay, so when I do my experiment now, I'm gonna start in some state, and I'm going to shake this, and then I'm going to look at this as before, as a function of pump probe time delay, and I'm going to look for features in the terahertz spectrum perpendicular to the planes that are indicative of either stronger or weaker superconductivity. Okay, so this is the experiment. I come with a vibrational pump which is resonant with the 600 wave number stretching mode in the planes. I cross my fingers and I hope to melt stripes. And then I will come with a second probe pulse, which will probe the reflectivity perpendicular to the planes in a system that at equilibrium does not have a plasma edge because I'm in the normal state, and I'm going to hope to see the appearance of a plasma edge. This is the protocol. And I'm going to say that if I see a plasma edge, I can at least write a paper where I say that I have seen the formation of a superconducting state by melting of this stripe order. And into zero order, this turned out to be a very satisfying way to do this, because I could, this is something I've already shown you. You take optimally doped LSCO, you cool it below TC, and you observe a plasma edge at 2 terahertz. And then you now take europium-doped strontium cuprate, lanthanum strontium cuprate, which is a 0.1 Kelvin superconductor. I excite this phonon, and I go from a featureless reflectivity to a reflectivity that has an edge exactly at the same frequency that I find in the optimally doped lanthanum strontium cuprate. Okay? And so this only happens when I excite this phonon, and I can kind of wave my hands and decide that this is indicative probably of melting of stripes, but certainly of coherent transport with very, very high mobility. The fact that I have a plasma edge at 2 terahertz is indicative of the fact that I have very high mobility transport perpendicular to the planes at a density which is exactly the same as the density of Cooper pairs in the optimally doped compounds. So this is what this experiment shows. And for some people in the audience, the appearance of a new mode that was not there before is also indicative of breaking of one particular symmetry, because the number of modes has gone up by 1. So although I don't know which symmetry I'm breaking, because there's a new zero crossing of epsilon 1, it means that I have a lower symmetry than the initial state. This is actually very clearly observed if I plot epsilon 1 in the transient state. Remember, the plasma edge is there because epsilon 1 crosses 0 at one particular frequency. And I can see how the zero crossing of epsilon 1 is observed actually to really high temperatures compared to, this is a 0.1 Kelvin superconductor with a charge ordering temperature of 80 Kelvin. And what I can show you is that epsilon 1 keeps on crossing 0 at all temperatures that are far above, this is reflectivity, this is epsilon 1, that are far above the equilibrium transition temperature. And in fact, details aside, I can observe a finite edge all the way to exactly the charge order temperature at this 1/8 doping. Okay, so this is again something that is satisfying in the sense that nobody's really too surprised by this. I have stripes. There's nothing that doesn't tell me that if I melt those stripes, I should have a 80 Kelvin superconductor starting from a 1 Kelvin superconductor. Okay, am I really melting stripes with light? The way one does this is, remember, I told you before about experiments with free electron lasers. If I use free electron lasers, I can measure the lattice positions. But what I can also do is to try to look at charge and spin order. And I can do this by measuring, for example, diffraction in the soft X-rays by looking at superlattice peaks that are indicative of order that develops in the plane. And I can do this if I go resonant either with the oxygen edge, oxygen K edge, or with the copper L edge. I can look at some superlattice peak that is indicative of the appearance of stripe order. Okay, this was only demonstrated at third-generation synchrotrons in the early 2000s. There's this very beautiful paper by Peter Abamonte and George Sawatsky who saw this very clearly in LBCO by looking at this superlattice peak. And one of the important things is that this is an extremely weak peak. I'm looking at a superlattice modulation of a forbidden peak by, say, 1/10 of a charge per site. So only by going resonant at the edge, I can have a diffraction peak that is only 10 to the minus 9 efficient. And this is the reason why if I want to do the femtosecond X-rays, I need something very special. I need a source that has a lot of photons, that is tunable to the copper oxygen edge in this case, and then makes short pulses that can be synchronized to the vibrational pump and then can be moved in time. So this is actually quite amazing that free electron lasers allow us to do this. So we brought a laser write the proposal gets rejected, then we write it again, etc., etc., etc. After a year, we could do this experiment at the LCLS, where we would pump the vibrational mode in LBCO, which is not the same as LESCO, but we're gonna, for the purposes of this talk, we're gonna make it look like it's the same. And then we probe the appearance of stripe order by this oxygen edge measurement at this superlattice peak. And we do an experiment, and so what we show is that by pumping this phonon, you start from a peak that is indicative stripe order, and immediately after excitation, this peak goes, let's say, to a level that is consistent with almost zero, a small number. So the stripe order is almost completely melted. Okay, and so what we can conclude is that, again, if we accept the fact that these are two slightly different compounds, to zero order, I can think is that melting these stripes on the same time is consistent with the time scale over which I observe the formation of this coherent coupling between the planes and the superfluid density. So here I'm plotting the superfluid density as a function of time that goes up in about 1 picosecond, and here I'm melting the stripes that go down within 1 picosecond. So to zero order, this is something that we can accept. Yes?
Well, even though you say that you observe this up to 80K.
Yeah. LESCO, yes. Right. You mean the zero crossing of epsilon 1?
Yes.
Yeah.
Yes, but that material has a equivalent TC of 35K at most, right?
Yes.
So the fact that you can observe this at 80K is already surprising.
Sure. No, absolutely. Absolutely. Okay, fine. Absolutely. What I'm saying, the reason it is certainly very surprising, but if you decide that in reality this material has got some charge order above TC, and this is depressing superconductivity sum, let me show you. Actually, let's look at the size of the size of the peak. Where was this? Yeah. So this is really has got a TC without the error of 0.1 Kelvin. Okay, the size of the edge is really nicely formed there, up to 25 Kelvin. But there is actually, we've checked this very carefully, there's still an effect at these higher temperatures in the light-induced states, which are, yeah. And you can see this, this is the epsilon 1 consistently crosses zero at temperatures higher than, okay, this is 30 Kelvin, so this is consistent with the 38 Kelvin of LSCO. Yes?
For YBCO, you can go to T star.
I'm getting there. So the next question is, can I do this in other cuprates? So I'm getting to YBCO. Yes?
More or less the same. It might be that you are fluctuating pairs, but not the real superconducting state.
Yeah, absolutely. Any of the above.
So you will detect if there are fluctuating pairs forming, this will be seen as an
That's not something I'm saying. Okay, let me just be very careful. What I'm saying is that if I take a system that is not superconducting and I drive the phone on, I observe signatures of superconductivity, and up to now, so we can get to fluctuating pairs in about 10 minutes. Up to now, we have told you that this happens when static charge order is being melted. This is what the 1/8 experiments tell me. And in principle, one doesn't need any fluctuating pair. One needs some stripe order that is either some sort of quasi-superconducting state or some enemy of a superconducting state. Okay? So let's see. You can take YBCO, and there's at least two things that happen in YBCO that have been discussed over the past few years. One is, this is one of the new, the flavor du jour, is the appearance of this charge order peaks all the way to, say, 150 Kelvin in YBCO. For example, in YBCO 6.6, which is again the same 1/8 doping, close to 1/8 doping, one observes the appearance of a peak in the soft X-ray diffraction that is indicative of charge order all the way to, say, 150 Kelvin. And the second thing are these very beautiful optical experiments that are suggestive of pre-existing pairing or pre-existing interlayer tunneling fluctuations between the bilayers. Okay, so there is some degree of evidence, at least, in the optical spectra that one could think of a precursor superconducting state that comes from the appearance of a mode that would be in principle related to these fluctuations between the layers. So the other thing that one knows about this compound is that it's quite well established that the position of this specific oxygen mode appears to correlate strongly with the TC in all cuprates and in the YBCO as well. So without really knowing what we're doing, we could decide that we could take YBCO, go to temperatures either below or above TC, excite this apical oxygen mode, and then decide that we want to either see a reduced superconducting state or an enhanced superconducting state. Okay, that's the protocol. So let's see what we see below TC. This is the experiment. We come and we pump this apical oxygen mode. The apical oxygen is one of the oxygens that is between the bilayers. So these are not atoms that participate, that are part of the superconducting layers. But we excite this mode in an oscillatory fashion, close to its own equilibrium position, and then we probe with a terahertz pulse, and we look at the signatures of coherent transport perpendicular to the planes. Now, this is a bilayer cuprate. So unlike the other cuprate in which I had single layers, remember I talked to you about these LC coupled structures. This is a bilayer. So what I will have are pairs of junctions. So if I take out every phonon, everything else, I have two modes there. One that is related to tunneling between the bilayers. This is a long Josephson junction with weak coupling, and so with an inductor that is large, and so with 1/LC that is a small number, and hence this would be related to this plasma resonance. This is a calculation, by the way, to a plasma resonance at low frequencies. This is the inverse. This is the inverse of epsilon1. That tells me there's a zero crossing of epsilon1, and then I will have a second peak. A second edge you can kind of make up here for various reasons that I'm happy to discuss later. This is a broader edge, and this edge is related to tunneling between these closer spaced junctions, and this is at higher frequencies because the tunneling is stronger. Okay, so now what we're going to do is we're going to pump the apical oxygen in between, and we're going to look at the features related to this low frequency edge, which is very sharp and very clearly defined, and is usually at equilibrium, is there only when the superconducting state is there. Okay, so these are measurements that we do on our samples. These are three edges that you observe at equilibrium below TC in these three compounds. This is the 6.6. You can see this is the 12.5 doped 1/8 compound. This is broad because this is coexisting with a charge density wave. So the tunneling is complicated and it's broader. As you dope it less, the frequency of this tunneling shifts to the red. This is because I have less Cooper pairs, and so the frequency is less, but also becomes sharper because this is a better defined. This is widely documented in other papers. Okay, and so the first thing we do is we go below TC and we excite the apical oxygen, and we look at this edge and we want to see whether the edge shifts to the red, meaning that I'm making superconductivity worse, or it shifts to the blue, which means I'm making at least the interlayer tunneling better. Okay? These are the differential measurements in reflectivity, and if you recalculate the whole thing, what you find is that there is a blue shift of all these three edges. This is actually clarified better if I plot now the optical conductivity, which actually is something I've discussed in the last lecture. What you really want to look at when you think about the strength of superconducting coupling is the way the inductive conductivity looks like. According to the London equations, or to just the basic superconducting equations, sigma 2 in a superconducting state is supposed to diverge to low frequencies like 1/omega and become infinity at zero frequency, where the Meissner effect is found. And the 1/omega-ness, the way this sigma 2 is diverging is indicative of how strong the superconducting state is. Or, in other words, the way this diverges is related also to the spectral weight in the delta function of sigma 1 and the position of the plasma edge. Okay, so a plasma edge shifted to the blue means that this thing diverges stronger. Okay, so at equilibrium, which is where everybody agrees that this is an equilibrium superconducting state, sigma 2 looks like this. You have this pitifully small divergence down to these frequencies in sigma 2. You have this other small divergence in sigma 2 in gray. When we photoexcited, we see clearly a very strong increase in the out-of-plane coupling between the layers. Okay? And all this spectral weight, okay, so this is indicative of the fact that below TC, when I pump the apical oxygen, the system becomes more superconducting perpendicular to the planes. And actually, the way the spectral weight is found occurs. This is a measurement done by Wanjiang Hu, who's a postdoc is still a postdoc in my group. What she found is that all this superfluid, this is a fit here, but the superfluid density that is acquired at low frequencies when I excite, all comes from the strength of this other peak, as if I was transferring coherences from this junction to this junction, okay? Yes?
So the sigma is measured along the z direction?
Yes, yes.
In principle, if you were to measure along the in plane, you would
Yeah.
expect something similar, no?
So this is exactly the question. One of the questions, okay, but this is right on the money, so I should have explained this better. In principle, what you could say is the following. The fact that I see that the Cooper pair tunneling becomes stronger perpendicular to the planes can be a consequence of the fact that the total number of Cooper pairs is getting larger. If that were the case, you would expect the in-plane sigma 2 to go higher, exactly as you say. Okay? This is, by the way, I'm not showing you the data, not what happens. As a matter of fact, the system becomes slightly more resistive in the planes, but it stays broadly the same. So in principle, this means that the number of Cooper pairs has to be approximately the same. Okay? What Van Jeng has found in this paper is that all the spectral weight that you gain here comes from a redshift of the spectral weight of the second junction. And the sum of the frequencies of this junction and this junction, the sum of the square of the frequencies stays constant. So in principle, just one second, you're stiffening this junction by weakening this other junction. And in principle, you seem to be conserving spectral weight. This is the observation we've made up to now. Yes?
No, but I didn't get exactly the point about the in-plane sigma 2. What happens to in-plane sigma 2 when you do this above TC?
Nothing. Oh, above TC, also nothing, pretty much.
Seriously?
Yeah. Well, at least nothing in the sense that we weren't able to see anything, which are two slightly different statements, but to first order 0, right? Now, in-plane measurements are hard in cuprates because the equilibrium reflectivity is extremely high. So I can elaborate a lot why these measurements may not be reliable, the ones in the plane. You're measuring changes in reflectivity from something that already has a 99.9 static reflectivity, so it's very difficult to phase, and there's all sorts of reasons why this could be wrong. But we were not able to see any change in plane.
Can you conclude from that, or infer, it's better, than what happens is the creation of Cooper pairs in the antinodal region? No?
No, I can't. The only thing I'm saying that I can say is that the total coherent spectral weight perpendicular to the planes appears to be constant, below TC.
I guess the background behind this question is that the tunneling mechanism is stronger at the antinode.
Yes.
Yeah.
If you see only the sigma.
Okay, that's a very interesting. I have no opinion on the matter. That may be a very good way to think about this. That this is really has got to do with the antinodal. Yeah, fine. No, that's fine. No. I actually don't know enough about this, and I'm happy to take. Okay. Okay, that's an interesting point. We should talk more about this. Okay. Okay, so this was now below TC. Okay. Above TC, you go in this state in which there is no tunneling between the two junctions. You excite the apical oxygen, and what you observe is so now below TC, we observed an equilibrium plasma edge at this frequency, and the loss function, which is the inverse of epsilon1, peaked at the same frequency. When you photoexcite this, you observe an edge exactly at the same frequency which you observe below TC in the same compound, and you observe a peak in the loss function exactly at the same place, indicative of the appearance, like in the Lesko case, of transport with very high mobility at the same density as the transport given by the Cooper pairs below TC. Okay? So, yeah, this is 2 times above TC at about 100 Kelvin. But so far, this is still a 1/8 doped compound. So this observation is equivalent to the observation that I already showed you in LESCO. Okay? And also, if you take the charge order peak in this compound, which you can measure, again at the X-ray free electron laser, after lots of struggling in trying to get beam time, and this is a static peak now you can measure in these experiments, you can see how this static peak goes away at the same temperature where our light-induced plasma edge goes away. And furthermore, if you do a pump probe experiment at the same laser on this peak that tells you about the charge ordering in 1/8 doped YBCO, you find that also this charge order goes away. So once again, at 1/8 doping, the observation in YBCO is the same as the one that you make in LSCO. spectral wave transfer between the two junctions notwithstanding. Okay, so that's of course that's an additional piece of information, but in terms of the fact that you can observe this effect all the way to charge order, which in this case is 150 Kelvin, as opposed to 80 Kelvin in the other case, and then the two effects, and that the melting of this order by, okay, this should be 40% of this peak, look at this, anyway, so this is almost the whole peak that is being melted, etc., etc. Okay, so far everything is like in LESCO 1/8. What's really surprising though in YBCO is that if you now go toward underdoped regions where the charge order temperature goes down, you would expect the light-induced plasma edge to be observable only to lower temperatures. And this is not what you observe. What you observe when you go to lower dopings is that you observe a stronger effect. This is some fit that I will not, something that is related to the size of the effect. And you observe the effect all the way to, say, room temperature or so. This is what made these experiments extremely controversial, but nevertheless compelling and exciting. That although the charge, so this is the YBCO, this is the YBCO 6.6 where we observed an effect that disappeared at the charge order line. Whereas when you go underdoped, although the charge order line goes here, you observe this effect all the way to much higher temperatures. So it's not really clear what's going on. Okay, what is going on in this material? So everything, I haven't told you anything about what the lattice is doing. If you remember the first part of the lecture, I had all this nice theory that at least helped us to rationalize some of the phenomena that we observed in the manganites. And in principle, I could use the same nonlinear phononics to try to understand what's happening to the lattice in these materials. I mean, I've been waving my hands about melting charge order, but we haven't done any serious measurement of what might be going on. Okay. So this I'm now going to tell you about results. These are a mixture of experimental results and theory work done by Alaska and primarily, and also sort of with Antoine, and that helps us sort out what might be going on in this material. So you take YBCO, you excite this B1U mode, which is the apical oxygen, and this couples to one or more, because this is a medium, this is a singly degenerate mode in a medium that has inversion symmetry. So this was the case where I had a boring sign before. This couples to one or more A modes of the crystal, okay? And it turns out that this actually couples to 11 A modes through this Q square Q mechanism that I told you about before. And this coupling to the A modes is in fact strong for 4 modes and medium for a number of modes and weak for, say, 4 modes. Yeah, I forgot which one is weak and which one is strong. But the one that is strong are these, so this tells you when you excite the B1U distortion, the apical oxygen distortion, by a frozen phonon, by a frozen amount, how much the equilibrium position of each one of these other A modes shifts due to this Q square Q coupling. And you can see that in some cases the shift is small, but in case of these guys, which are rather sloppy potentials, the shift can be very large. So we identify 4 modes that are important in this to this order, and then we also identify higher order contributions that I will not tell you about, but we've done measurements where we could exclude that other contributions like the Q square coupling would be important. But in principle, if I believe Alaska's calculation, and I believe that the B1U mode couples strongly to only 4 modes, and I believe normal mode calculations, all I have to do is to measure 4 structure factors at the free electron laser, and with those calculations can reconstruct the whole unit cell of 27 or 29 atoms as a function of time. Okay? So one of the most beautiful things is that if you measure 4 peaks, and you can work with Alaska's calculations, you can fit all these 4 peaks by using only one free parameter, which is the distortion of the B1U mode, which of course is the mode that we're driving directly, which is a number that we don't have under control. Once you assume that, you can use all the other coupling mechanisms, and the peaks that are supposed to go up, and the peaks that are supposed to go down, and they go up and down in quantities that are of the right ratio. Okay, so this gives us some degree of confidence that we can take these 4 peaks and we can use them to reconstruct all the position of all the atoms transiently, okay? With all the caveats that I've given to you, we now have a molecular movie of the unit cell structure as a function of time in this putative high temperature light-induced superconducting state, or whatever this is, okay? So the features, this is a new transient crystal structure that, let's say, at this point in time, the crystal is distorted by some percents, one way or another. And the important features, there's a couple of important features. There's changes of the buckling in the planes, which is slightly different if you look along the x or the y direction. There is a motion of the apical oxygen toward the planes, on average, and a number of other features. And also the observation that, I'll tell you later, other observation. One important thing that I want to point out, actually, is that these changes are actually very similar to the ones that you observe statically when you apply static pressure. There's a number of experiments that have been done statically. This is where people have measured, for example, pressures up to a degree where the crystal would crack. And they would have observed, for example, motions of the apical oxygen by about 0.5% on average in the same direction in which we observe it on average, except that we can drive it by, and this number was connected to a change in critical temperature by, say, anywhere between 5 and 15 Kelvin, depending on the details. Okay, by phononics, we could drive it in some cases between 1 and 3%, and this might be indicative that one of these, that some of the same physics on average might be happening. The second thing that happens is that one observes the fact that some atoms walk apart within the unit cell, which might explain why the tunneling between these planes was getting weaker. And these atoms become closer between the bilayers, which might explain why the Judson coupling was getting stronger between the planes. So this in principle is also a good thing. And at least, and it's not really clear how finely tuned this is, but at least under our circumstances, one could can do LDA calculations and measure exactly where all the bands are and convince oneself that all this would give rise to a self-hole doping of the planes due to the changes of the Fermi surface and its area. Okay, so there's at least 3 good things, unclear what is causing what, that happen along this direction that are indicative of a better superconductor. Okay, and this is, what of these things is important and what not is not really clear, and we're falling in the same category of trying to understand equilibrium spectra of superconductors. What I would like to do now, though, is to reflect in a different way about how a modulated cuprate might react. So let's go back and think about the same problem in a slightly different way. Okay, so what I told you is that below Tc, what I would find is when I accept, these are 2 order parameters on the planes, what I would find is that the coupling between the planes, so these phases between the planes, would become more correlated. Okay? Let's think about this. Let's think about 2 pendula. Okay, how does this work? There you go. So these are 2 pendula, and now I'm going to start oscillating one pendulum close to its pivot point. When you take a pendulum and you oscillate it close to its pivot point, what you find is that the temperature of the pendulum, when it's being shaken, becomes lower. This is because the potential becomes sharper, and the frequency becomes higher. So maybe what one could think of is a situation in which I'm modulating this particular coupling, which is this particular oscillator, and what this is doing is blue shifting the plasma resonance simply by modulation. Okay, so this is another way to see a modulated state, perhaps in a sort of hand-waving way, but understanding why these edges and these planes might become more coupled when they're being driven. What's very interesting is if you think about the same pendula above Tc. Let's assume that above Tc, I can think about a superconductor as something in which I have some finite order that is, however, fluctuating, and the correlation between the planes.
Here your 2 modes, you identify them as a charge and superconductor?
No. what I'm saying, you mean in the previous example?
In this example, your two hours.
These would be 2 order parameters on the two. This is density and phase on two planes, and the 2 phases are correlated by the Josephson coupling, right? And I'm thinking about oscillation between those phases as the Josephson coupling, let's say, okay? So let's think about this effect, and let's assume that above Tc, I retain some finite pairing amplitude, and the reason why the system is not a good superconductor is that this phase is going around and the 2 phases are uncorrelated. So let's do the same game with the Kapitsa pendulum that I showed you before. Imagine 2 pendula that are rotating and start modulating one. So if you take the Kapitsa pendulum, okay, this is above Tc. You see the phases are uncorrelated, and then now I turn on modulation. And what the modulation does is, for the same reason that I saw before, it traps the phase and it makes the planes correlated. So in a sense, there are some genuinely dynamical phenomena that, that perhaps are only tangentially related to the physics of cuprates at equilibrium that might explain why a time-dependent modulation in a system that does have some finite bosonic entity above Tc might be useful to correlate those, okay? So this is, again, it's perhaps a qualitative argument, but it's something that one should keep in mind when one thinks about non-equilibrium phenomena in these materials. Okay, Antoine, how much time do I have?
Good question. Something like maybe 17 minutes.
Fine. Right, okay.
I have a question.
Yes, please.
Is there anything you could do to probe magnetic correlations within the plane?
I mean, of course, one could probe static magnetic correlations in the way that I told you by scattering, by resonant soft X-ray diffraction. But you are thinking about something different, aren't you?
No.
So the answer is I can do resonant X-ray diffraction and measure, provided that they're reasonably long range, so 2, 3, 4, 5 unit cells, and they form a peak. In principle, I could measure those. And, I'm not a super expert of these measurements. I'm not sure how courageously you can fit those peaks. But in principle, one could try to look at with the caveat that you're looking at a non-equilibrium system, and we should talk to somebody that knows about these things. The other thing is that in principle, if one could do a Rix experiment, what you could look by looking at the dispersion of some Rix peak with momentum, you might be able to back out, for example, if the super exchange interaction becomes stronger, then the dispersion of your Rix peak is going to become different. So that's perhaps the crispest way to do this, provided that the experiment can be done, but there are some advances in this direction. Okay, so let's see, last topic. Is this phenomenon specific to the cuprates, or is it more general? I mean, what I've discussed, of course, are cuprates, which not only are very difficult to understand, but are also materials in which there's many things that are special, including the fact that the interlayer tunneling, although it might not be the driving mechanism, as some have suggested at some stage, it is nevertheless related to the whole business so if one thinks about, lots of people, normally theorists, ask me, can't you take a normal superconductor and do the same? Of course, if you take a normal superconductor like aluminum or mercury, these materials tend either not to have optical phonons, and therefore not to be easily modulated with light, or to, not to be simply conducive to experiments like this. But one in principle can take materials in which one has very strong optical phonons that are very different from cuprates, and nevertheless one could do a similar experiment. So another material that we've focused on, and this is really something only for the next 10 minutes, is this potassium 3C60 superconductor. This is one of a family of doped fullerite superconductors. In this particular case, one finds oneself in this is not the highest temperature superconductor. The cesium material is more correlated, and under pressure has a 40 Kelvin transition temperature. But in this case, one has at ambient pressure, one has a 20 Kelvin superconductor. It's an FCC lattice of buckyballs, which are doped 3 times by 3 potassium atoms. And so one has a physics of this FCC lattice of 3 times doped buckyballs that become superconducting at 20 Kelvin. Okay, so this is observed, for example, statically by measuring conductivity or by measuring the size of the gap, which follows a very nice mean field behavior. If one wants to look at AC features of the superconducting state, one can look at, in some crystals, which are the ones that we're going to be using, one can look at the optical properties of these powders of potassium 3C60. And so let's see. So the red curve is the reflectivity as a function of wavelength taken at the electrosynchrotron in the metallic state at 25 Kelvin. And one here observes a reflectivity that is about 90% and some sort of plasma edge at this frequency here. And when one cools statically below Tc, one observes a transition of the reflectivity to about 1, to exactly 1, below the gap. Okay, and this is observed more clearly if one looks at the conductivity features. Again, the red curve is the normal state conductivity, where the real part of the conductivity has this Drude feature and this polaronic peak. Whereas below Tc, one finds the superconducting gap opening very clearly below 6 millieV. And more importantly, or as importantly, a divergent imaginary part of the conductivity, which is indicative of a delta function at 0 frequency in the real part of the conductivity. So these are features, again, in the AC spectrum, especially the divergent sigma 2, that are considered to be indicative of the superconducting state. Okay? And much clearer in a general sense than the plasma edge, where one, although they're probably similar, at least at the intuitive level, they're easier to digest. And the reason why this happens, you know, there's been a lot of discussion, but all I'm going to tell you is what has guided us through our experiments. And I will leave this a little bit up in the air at the end because this is being studied a lot. What is known is that on-ball vibrations, especially those of this five-fold degenerate symmetry of the Hg mode symmetry, are helpful in reducing up a putative high spin state into the formation of singlets in one of those orbitals. Actually, one occupies 3 of these reduced orbitals that beat with one another and give rise to this type of superconducting state that more advanced theories have explained as a form of Jahn-Teller activated negative Hund's coupling. So what we want to do is then drive, what we started thinking about was to drive these vibrations, or something that was related to this mode that was known to drive, to help superconductivity, and try to activate this by nonlinear phononics and see if we could increase Tc. So what we did here, and again thinking about in this way, which will probably not be exactly what the mechanism is, we excite this T1U mode, which is observed clearly only in the single crystals, whereas it kind of disappears into the polaronic peak that I showed you before in the powders. Excite this mode to large amplitudes at about 7 microns, and then rely on the coupling between this mode and the H modes to perhaps deform the lattice along the direction that is good for superconductivity. So the experiment is the one that I've been telling you about for the last 2 hours, one in which we have a short mid-infrared pump that elongates these buckyballs along this direction. And then we have a second pulse that comes and probes the reflectivity in the gap region, which is where I observe a superconducting gap by cooling. And I start in the normal state at, say, 25 Kelvin or even 100 Kelvin. Remember the red curve. And I'm going to try to induce the blue state, which I could do only by cooling previously. And this is really a very satisfying observation, at least as far as I'm concerned, one in which one shows that at 25 Kelvin, one can take the red curve, cool it below Tc to 8 Kelvin, open the gap and give me the divergence. Or one can decide, one can turn off the fridge and excite the phonon, and one observes the formation of a gap that looks quite similar to the one we observed, only up to a value which is at least, say, 2 times bigger than the equilibrium gap. And this is observed, in this case, at 25 Kelvin, so 5 Kelvin above equilibrium Tc. And even more strikingly, is observed even at 100 Kelvin, 5 times above Tc. And you can see the gap here in its full glory in something that is really very strongly suggestive of if this is not a superconducting state, it's something that has clearly the same optical properties as an equilibrium superconductor. And actually a really remarkable conductivity at low frequencies, okay? And this effect, you know, is observed. The opening of a small gap is observed for all temperatures, you know, up to even room temperature, although the gap becomes less and less convincing as one goes to temperature higher than, say, 100, 150 Kelvin. There, in principle, one can fit the data with a Drude fit with a slightly better mobility than the equilibrium state. Okay? There's actually more recent experiments under static pressure that actually suggest that this state is not a trivial matter at all, and might in fact be indicative of some non-trivial coherence. Okay, but this is really subject for a different and more specific lecture. Okay, so there seems to be a crossover in some non-equilibrium sense as I change the basic temperature between a state in which the light-induced, let's say a light-induced superconducting-like state and a light-induced high-mobility metal-like state. Okay, and there's no clear transition between the two. And this is really, again, the observation. I pump this phone on, and I observe the opening of this gap. Right, so again, now I'm just gonna give you some ideas of what people are working on, although this is really not clear at all. I'll tell you what we were thinking of at the beginning and how things are being discussed. What is going on? Again, if you look at the equilibrium electronic properties of the system, as I told you, there's these these triply degenerate electronic states which are occupied in the doped buckyball. So if you take a non-doped buckyball, the highest occupied molecular orbitals are these here. If you dope it 3 times, you'll put 3 electrons on these bands. And now the question is, how are these bands, which again, as I mentioned before, are susceptible to the Ian-Teller distortion, how do they couple to the driven T1U mode that I'm driving? You know, there's basic consideration that tells you that this mode doesn't couple to these electronic levels directly, but that in principle, if I take the Q square Q coupling that I told you about before during the whole first lecture, I can displace the molecule along this HG coordinate just by simply considering that the square of this T1U couples to HG. So that's what has guided us, and at the beginning, what we thought was that perhaps one could consider a type of excitation in which, again, I am driving this T1U mode with 0 average, and then this is coupling to one or more of the H modes and stabilizing this paired state. Okay. Another thing that is probably more appropriate has come out by thinking of what other types of couplings might be taking place. Again, we have done other experiments that I didn't elaborate on today, where we considered how the Q square coordinate of a driven mode might couple to the on-site Coulomb correlations that one finds on the molecules. Okay, and the reason why this is a mechanism that might be particularly important in the molecular crystals is that when one distorts a molecular mode, if one considers localized molecules, one has a whole vibrational ladder that one can populate, just in the same way that in chemistry one thinks about these vibrational ladders in the electronic ground state. And therefore, by exciting one infrared vibration, one can change the volume of the molecular orbital and hence change the Coulomb integral. Okay, so in principle, by climbing the ladder, I'm making my electronic cloud bigger, and hence U is, in principle, should go down. Okay, and this was something that we showed in this paper where we took a completely different compound. This is one-dimensional ET compound in which by exciting these molecular vibrations, we could show that the Mott gap was being shifted on average to the red and was being modulated at twice the frequency of the driving mode. So again, suggestive of the existence of this Q square U coupling in the buckyballs. And so perhaps one can think about these mechanisms in this particular compound, in which of course Coulomb correlations are extremely important, but these are Coulomb correlations in which one, in a way in which one is interested in the correlations that occur over 3 orbitals of this triply degenerate small T1U mode that I told you about. And there's actually very interesting calculations in the first paper by Min-Jae Kim and co-workers here from the Collège de France Polytechnique group, in which it was suggested that actually this one could reduce 2 out of 3 orbitals to a lower state with respect to the energy of a 3rd orbital, and hence enhance superconductivity. And there's actually a time-dependent calculation that is just being submitted that reinforces these ideas dynamically. And there's many other ideas that are kicking around to explain these experiments, but I think this is beyond what is expected for a lecture of this type, and I will leave you with the not even a summary of the last 2 hours, where I try to advertise the wonders of nonlinear phononics, and how, for example, the excitation of nonlinear phonons can be used to distort molecular crystals, can be used to control the tunneling in some cuprates and enhance some superconducting properties, can be made to make atoms rotate in circles and hence break time reversal symmetry, can couple to stripe order, and can do many other beautiful things and I believe we're just at the beginning of something that, if one looks at the development of nonlinear optics, what people can do in coupling electromagnetic modes with one another, in principle, one could use this as a new platform for materials control. And I thank you for your attention. I hope some of the things came across clearly enough. Thanks.